So this session is actually a continuation of our previous session on decision trees. So we're just gonna be like clarifying few things and then like add few more points. So yeah, let's get into this. To brush it up, so we all know decision tree is a supervised algorithm. It's kind of a basic algorithm for a lot of algorithms which comes into this banner. It works for both regression and classification problems. Okay, so we all know how the tree looks like. So yeah, let's skip this and then yeah. So we have been discussing about how trees split, right? We discussed in the previous session how trees split based on chi-square, Gini index, entropy, and on variance. So though we have like discussed all this, how it works, how a tree is developed, and how we can like find the implication of the tree and get a result out of that. We have already did that, but when we like use it in the practical uh, application. So we really call use the function CHAID, which stands for chi-square automatic interaction detection. So in this method, chi-square is used. So only if we have categorical data, we actually go for chi-square method. Okay. So at that time, you will be like developing a tree based on CHAID, which is always called chi-square automatic interaction detection. So, and we have a function called a banner called cart, which is uh, otherwise called classification regression trees. So under that, people will be like using techniques like Gini impurity index and entropy or information gain, and some of squared errors. I mean, in case of regression, we go for the reduction in variance method, or I mean, which is your sum of squared errors that we use only for regression, and Gini impurity index and entropy is been used for classification trees. So this is there are a lot of various impurity measures are available, but there's two impurity measures like Gini index and entropy is like it's been widely used. Okay. So with this information, I think you'll be able to understand how um, decision trees works completely. We already discussed how KAIS works and how it has been used in tree formation, how Gini index been used. All these things we have discussed. I've just added a screenshot here, and examples have been removed. If you want, you can just go to the previous session text and then review all that. Okay. So here we'll be just working only on the probabilities of both the events. So it just works only for binomial classification. Here chi-square, as I told, it works for chi tree, and entropy or information gain. It's also helps you to form a decision tree structure and gives you a very beautiful tree at the end. And reduction in variance, your sum of squares of error, SSC, which is which is really used for building trees for regression problems. Okay, so we have been already discussing this in very detailed manner with each of the examples. So we'll be skipping this and moving to another small topic called cost of misclassification. So this is actually, it's kind of one of a measure which has been used in tree formation. So this cost-based splitting criteria is very much used when you are using a very sensitive data to work on decision trees. Okay, so here we will be assuming that there is a penalty for misclassifying. Okay, so this penalty of this misclassification is assumed. Okay, it's based on the business knowledge. The subject matter expert will be assuming the cost of misclassification. So here we are just having a sample for confusion matrix table format here. So we have predicted 1 and 0, observed 1 and 0. So for here we have classified 1 as 1. So in that case, if you're going to do that, we are not going to do any penalty because things are right. if you classify 0 as 0, we're not going to give any penalty because it's been classified right. So in case of classifying 1 as 0, we are giving a penalty of 5, and in case of classifying 0 as 1, we are giving a penalty of 1. Okay, so maybe we can take an example of like, we're trying to predict whether the loan has to be like sanctioned for a customer or not. Okay, so here it says 1. So here we have to like, it's a positive result. 1 is a positive result. So we say the loan has to be sanctioned, but it was kind of denied by the algorithm. So it's so here you're assuming the weight as 5. Here instead of 0, it has been like predicted as 1. So here the weight is 1. Okay, hope you are able to understand this. Okay. So in Python, you will be like using a function called error rate to mention this. You'll be like creating a list of all this you know misclassification cost, and then you can include that in your algorithm. Okay. And the next concept is Bonferroni correction. It's actually, it's one of the very simplest method is being used when you're like dealing with multiple hypothesis testing. We all know we'll be like, setting hypothesis when we deal with algorithms, right? So here we always assume our type 1 error rate is 0.05. Right? I mean, our we always assume the p value is 0.05. So we are setting the error rate as 5% because we are assuming that most of the time we are willing to. I mean, most of the time means like 5% of the time we are willing to accept a false positive result. But in some cases, it is 1%. It is actually based on the problem nature and the willingness of the SME. Okay, so here we're just assuming we are willing to accept 5% of a false positive result. In that case, so imagine we'll be like have to setting hypothesis whenever the node is kind of splitting in your decision tree algorithm, right? So there is a multiple hypothesis testing is happening. So in that case, we can't just keep our alpha at the same 5%. Okay, so we have to like employ a method to identify what is going to be our false positive rate. Okay, so for example, we are like doing this iteration for 7 times. Okay, so here 1 minus 0.05, which is our 95%. Since you're doing it for 7 times, you're like you're squaring that up for 7 times. 1 minus 0.05 to the power of 7. So you get 30%. So here, instead of like 5% of your type 1 error rate, you're using a 30%. Okay, so you're willing to accept a 30% of errors. Okay, so this is one of the major reason when you go for like too many splits, your data might be underfitting. Okay, so one of the major method which is used to find out the correct p-value is through this Bonferroni correction. So here you'll be like using the formula alpha divided by n. When for alpha we'll be like substituting our original p-value, which is most of the time it is 0.05 or 0.01, and divided by n, which is number of splits or number of tests is being performed. Okay, so when you're performing 2 tests, I mean, or 2 splits, your corrected p-value would be 0.025. For 3, it is 0.17, and it goes on. Okay, so there are various methods that's been employed to control your type 1 error rate, because like for 7% we got error rate is 30. I mean, for 7 splits we got a error rate is 30%, right, which is not really acceptable. So but we cannot like look into like decrease our number of splits as well. So there's a lot of various methods has been applied to work on this issue. This Bonferroni correction is one of the widely used and the simple method. Okay. So you got any questions on this? Maybe we can just discuss about this, and I want to have a clear understanding of all this so that you'll be able to perform better in your exams and lab theory.
Clear.